I will start this presentation by making a little survey. So I ask you all to take forward the green and the red card that you have, and I'll ask you the question, how many of you know what hypoxia is? And while you do so, I will come with this very bold statement that hypoxia is the most profound symptom of nutrient over-enrichment in the Baltic Sea. So please raise your cards. It appears that most people, I don't trust you. It appears that most people know what hypoxia is, and that actually makes my task a lot easier. So in Hyper, actually, we have reanalyzed a lot of the historical data that we have from various databases around the Baltic Sea to reconstruct the development of hypoxia in the Baltic Sea over the last 110 years. And what we can see is that it has in fact increased more than 10 times over the last century, from being confined to very small areas, mainly, as you can see on the map, around the Bornholm Basin, east of Bornholm, and also east of Gotland, up to about 1950. And in the 1950s, it more or less exploded, increasing to more contemporary areas of about, or of above 60,000 square kilometers. So that's actually quite a lot. That's about 1.5 times the size of Denmark. And it's actually also, if we take the central part of the Baltic, it's about 25% of the central Baltic that's affected by hypoxia. This has severe consequences for the animal life, because when we don't have hypoxia, we normally have what we consider to be a healthy ecosystem. We have a lot of animals that are living on the sediment surface or bury into the sediments. But now, in this area where we have hypoxia, and we have also anoxia, as Henrik just mentioned, we have basically no animal life, we just have bacteria. So this is what we call a dead zone. What we can also see is that this development, this trend that we have in the area of hypoxia, it's very consistent with the inputs of nutrients that we have, and I think that Marcus would probably present that from his project EcoSupport, that in the 1950s, nutrient inputs to the Baltic Sea really exploded. So this is very consistent. It's obvious that the development in hypoxia is related to nutrient inputs to the Baltic Sea. But it's not only just the open Baltic Sea that has problems with hypoxia. We also, in Hyper, found that hypoxia is widespread and increasing in the coastal zone. Actually, 1/3 of the sites that investigated in this study showed to have problems with hypoxia. And this is mainly around Stockholm Archipelago, the Finnish archipelago, and also the western Baltic Sea, in the Danish fjords, and also in some of the German fjords. Now, what's important about hypoxia, that is that it really affects the natural ability of the Baltic Sea to remove the nutrients that are fed into the system. I'll show this for the two most important nutrients, nitrogen and phosphorus. Now, on the left-hand side, we see a healthy Baltic Sea, and in this case, denitrification, which is the main process responsible for removing nitrogen out of the system, it's taking place in the sediments where we have lots of bacteria, and you have, you could say, a relatively efficient way of transforming nitrate into denitrogen gas, which then is removed from the system. But what happens when we have a hypoxic system? Now, in this case, the denitrification is not taking place in the sediments. Instead, it has to take place in the water column instead. And it's taking place in a narrow bound where you have a lot less bacteria. We haven't exactly quantified how much less it is, but it's potentially less than what can be denitrified in the sediments. If we look into the P cycle, what happens when we have hypoxic conditions, as you can see over here, that is that the P is buried in the sediments, not in the normal form as iron-bound, which happens under oxic conditions, but as organic P. And what will happen, and this is what we hypothesize, is that we have a potential phosphorus bomb. That is that in case that the parts of the Baltic Sea turn oxic, then a lot of this organically bound phosphorus will be remineralized and it will be bound to iron. But then, if the system turns hypoxic again, all that iron-bound phosphorus will be released to the water column again. And this means that oscillating hypoxic-oxic conditions, it actually reduces the natural ability of the system to bury phosphorus. But most important of all is that when you have a healthy ecosystem, a healthy Baltic Sea, you have animals living into the sediments, and they are quite important in terms of all this nutrient remineralization that we have. This is kind of a bit cryptic figure here, but the key essence is that there's a large difference between whether you have animals that bioturbate the sediment surface that more or less efficiently puts down oxygen into various zones of the sediments. And actually, in this case, what we have shown in hyper is that if you have animals, in this case, a worm called Marincellarium, which is actually an invasive species, the burial of phosphorus is much larger as when it's absent. So the worms are important. Give the Baltic Sea to the worms. But there are some bright spots around. And one of them is from the Stockholm archipelago, and this is from the inner part. And of course, in Stockholm, they've done a lot to, say, reduce the inputs of nutrients. They have implemented wastewater treatment on the sewage treatment plants, and they've also discharged some of the wastewater further out into the archipelago. And this is one of the cases where we have shown documented positive trends of hypoxia. So what has happened in the Stockholm archipelago is that we've had nutrient reductions, which has led to a reduced production of organic material, which then leads to reduced oxygen consumption in the bottom waters, which has improved the oxygen conditions to a state where suddenly the fauna can recolonize the system. And this has major implications for the biogeochemistry in the sediments. And this we have shown, and this is with this figure here. Now, what happened is this is again this invasive species called Marincellarium. Now, normally, this first period from 68 to 73, that was before phosphorus was removed in the treatment plants. But from 74 to 2004, there has been little discharge from treatment plants by phosphorus. So we have a very good connection between oxygen conditions and the release of phosphorus in the sediments. But what we see after after Marincellarium comes into the system is that we see that suddenly we have a lot less phosphorus pouring out of the sediments because the worms, the Marincellarium, bioturbate, bring down more oxygen and leads to a more effective burial of phosphorus into the sediment. So we have a more permanent sink with these animals. So it's important to re-establish the ecosystem where we have some benthic animals that help improve the system. And this is what I showed with this one. So, oops, I'm sorry, that was not mine.